And slope fields come up because they are a graphical representation, the flow of tangent lines, which are the slopes, for a family of curves. And it's of a family of curves of diffie-q's. Alright, here's a copy of the handout from your SlopeFields packet. And what we're going to do is construct a slope field for dy dx equals to xy over 4. Now here's our table that we can use to create our slope field. And I'm going to go ahead and write it here on the side. Dy dx equals to xy over 4. And the way that it works is we just plug in what all of these x and y values are into our equation for dy dx. So these are the x values listed across the top and the y values listed across over here. So for instance, when x is 0, you should be able to tell pretty quickly that dy dx is 0. And when y is 0, dy dx is also 0. So these are all lined up in here as zeros. And then the other ones are a little bit easier to work out. It's the product of the two divided by 4. So the product of x and y divided by 4, and just fill them out across. Negative 2 times 1, and divided by 4. And notice there's some symmetry in the numbers. So this here is 1/2. This is going to be a positive. So I hope I got all of those right. And what we're going to do now is over here on this grid, this xy axis, I'm going to draw little slope lines or tangent lines to represent these. Now I'm going to go ahead and make each one of these a scale of 1, and I'm going to draw them pretty small. What you do not want to do is draw really, really big long tangent lines, because then they start to overlap. You want to think of these as little lines like on the road that you follow. Okay, it's going to be a little path. So slope of 1/2. So that would be like up 1 over 2. And I have a slope of 1/2 in a couple of places. Over here and over here. Okay, so that would be like going up 1 over 2. So technically it should go through there. But we're not going to draw all of that. We're only going to draw it in this little tiny spot. So again, like this one. Oops, not that way. Should reach this point down here, but I only want this piece, so we get rid of this. And you guys should use a ruler to help you here. I can't really put a ruler to the computer, so it makes it a little bit tougher. This should have a slope of 1 up here, so I should make sure that it touches through to this point up here. I have a negative 1 right here, positive 1, negative 1, negative 1/2 here, and negative 1/2, negative 1/2, oops, a positive 1/2 here, and another negative 1/2 here, positive 1/2 over here. Again, keeping in mind that it should follow all the way through with the slope of 1/2. Okay, then we have a 1/4, should be flatter. This one goes flatter this way. Flatter and flatter. Okay, again, use a ruler. I can't use a ruler up here, so it's a little bit tougher. What I'd like to do now is, can you tell kind of what this graph resembles? What kind of shape? Almost looks kind of parabolic, don't you think? Almost seems like it would kind of fit like that maybe. Or like that. It's kind of hard to tell. But I'm actually going to have us over here on the side solve this equation. Solve this differential equation. So it was dy dx equals to xy over 4. A little bit tougher because this equation has a y in it, so we really have to employ what's called the separation of variables. I need to divide the y over, so I have dy over y, and move the dx over. Whenever you have a constant, I would suggest that you keep it on the side, on the right side. So 1/4 x, and then dx like this. So we're going to integrate both sides because we're separating our variables. And the integral of a y is, do you guys know? Natural log of y. But I have to put absolute values around it, because y could be a negative value, as evidenced by our graph here. We have y values that are negative, but we cannot have the natural log of a negative number. It doesn't exist. Think about the domain of our natural log function. Looks like this. There are no y values. So because of that, you must put absolute values around this. It's going to be incorrect and you're going to lose points if you don't do this correctly. Okay. Now I need to integrate 1/4 x, so that gives me 1/8 x squared. And then I have plus c. This c here takes care of the constants that are going to show up from both the left and the right hand side of my equation. Now I want to solve this. I need to find y. But so far I have ln of y. I don't have y. So we need to basically e both sides, take e to the power of ln of y and e to the power of 1/8 x squared. So the nice thing about e's and natural logs, they are inverse functions. So you're going to end up with just the absolute value of y equals e to the 1/8 x squared plus c. Now this plus c is part of your exponent. It is not a plus c on the outside. It's part of the exponent. So we can use our properties of exponents and rewrite this. I can rewrite this as a e to the 1/8 x squared. Now how can we do that? Because remember, if you have e to the x plus y, that's the same as saying e to the x times e to the y. We can separate those. So if this y happened to have been a constant, c, e to the c is now some new constant, and here I am calling it an a. All right, try to remember your properties of exponents. And now this y value is either positive or negative, because when you do the absolute values, you actually get two solutions. It's either positive or negative. So because I rename my constant, it's also going to take care of the absolute value portion of this. So this a will now either be positive or negative, depending on what your initial condition is going to be. Do not drop the absolute values until you are renaming a constant. All right, let's continue on with how to read a slope field. So some of you guys may remember some of this stuff from last year. Okay, so the first thing, when you are looking at a slope field, I want you to examine it along the vertical lines. So what I mean by that is if you are looking at the graph and it's got the same slope vertically, then that tells us something about the differential equation. Okay, what it means is that the y's don't matter. I know that doesn't sound very mathematical, but by that I mean whether the y value is a positive 1, a negative 2, 0, it's all the same. The slope field, or the slope value, is the same. So if the y's don't matter, then that tells you that dy dx depends on x only, that you're not going to have any y's in your dy dx equation. So similarly, we can look at the slope field segment along horizontal lines, and if they all look the same horizontally, and so by that I mean something like this, then that means for us the exact opposite. The x's don't matter, and that dy dx depends on y only. So those are two things to always keep straight. The other two things that are on here just really are having you deconstruct the slope field and what you're looking at. If you examine the slopes in quadrant 1, if they're always positive, then that means that x and y are both positive in that quadrant, so therefore you would have positive slopes. Anyways, we'll talk about those as we look at some examples. Okay, so let's take a look at this one right here. If you examine along the vertical lines, all the slopes are the same. So that means for us then that dy dx has only what in it? X's or y's? It should only have x's, because depending on what x is, if it's negative 1, then it has a particular slope. If x equals to 3, then it has a particular slope, regardless of what the y value is. Now what else? Some of you guys may notice that there are no negative slopes. So no matter what, dy dx is always greater than or equal to 0. So that's something also to note over here. Okay, so let's try to eliminate some of these choices. It should have only x's in it, so we can eliminate the first one and the second one. Now which of these two do you think it would be? 1/3 x cubed or 1/2 x squared? Well, look at our graph. Our graph does kind of look like maybe a cubic function, right? So should that mean that dy dx equals to 1/3 x cubed? You want to be careful here. You're looking at the slope field for the actual functions. So y maybe is an x cubed. But we want to find, notice here, dy dx. So if y is a cubic function, then the derivative dy dx should be a quadratic function, not the cubic function. Okay? Not to mention, we said that we want to have no negative slopes. How would we achieve that? By having an x squared in our dy dx equation. All right, let's try a couple more. So how about this one? What do you guys see? Well, it appears that all of the rows are the same. So what does that mean for us? It should only have what? It's only dependent on x. So there shouldn't be any y's in it. So let's eliminate our y's. And that's the only one. Now, should it have x's and y's in it together? No, we actually need to cross that out. Oh, this one's a little too easy. We can actually eliminate all three of those because they have both x's and y's in it. Darn, I forgot to change these answer choices. Okay, let's try another one. That might have been a little too easy. All right, number 2. Which of the following differential equations has the slope field pictured at the right? Okay, are all the rows the same? Are all of the columns the same? This one's interesting. It's a no. So that means it can't only have x's and it can't only have y's in it. Now this graph looks kind of like a circle, right? Kind of looks circular. So do you think it should be x squared plus y squared? It's going to be a no. Remember, we're looking at the graph of the function, which could be x squared plus y squared, but that means the derivative is not x squared plus y squared. So let's just kind of leave that there for now. Pretty sure that's not going to be it because I'm actually looking at the circle, but the derivative of that equation is not a circle. Let's take a look in quadrants 1 and 3. What do you notice about those slopes? dy dx is always negative here. How about in quadrants 2 and 4? dy dx is always positive. Now think about the x and the y values in those particular quadrants. Okay, could we have dy dx being a negative value if we had x squared plus y squared? No, that would always give us a positive. So it's down to one of these two. Which one should it be? Well, let's think about quadrant 1. In quadrant 1, x is positive and y is positive. So in order for us to have a slope that is negative, we need to have a negative sign in there somewhere. So that's going to lead me to choosing D as our answer choice. All right, now let's try the last one on here. Which of the following has the solutions pictured at the right? Okay, again, rows not the same, columns not the same, so I can eliminate C and D. What else do you notice? Well, in quadrants 1 and 4, we have positive slopes, and in quadrants 1 and 3, we have positive slopes, and in quadrants 2 and 4, we have negative slopes. Okay, and kind of looks like the slopes are doing what as we approach the x-axis? Looks like they're kind of flattening out, right? They're approaching a vertical tangent line as x gets closer to 0, and over here, as y gets closer to 0, it's approaching a horizontal tangent line. So what would that lead us to? Take a look here. Look, we have a fraction. As y approaches 0, it looks like it's horizontal. That would make sense. As x approaches 0, it looks like it's approaching a vertical tangent line. It's going to be this choice. Not to mention, if we have x plus y, yes, they're positive over here, and yes, they're negative down here, but what about over here? X plus y in quadrant 2 doesn't necessarily mean we have all negative slopes all the time. Same with quadrant 4. So we're going to eliminate that and that. So one other thing you guys will have to do is learn how to use the SlopeField program that I put onto your TI-84s. They can also be done on your TI-89s, but we won't get to learning how to use that for a little bit. So if you want to explore it on your 89, you can, but on your 84, you should be looking for a program called Slope or Slopes. I can't remember which one. And the way that it works is you're going to enter your dy dx equation, whatever it is, into your y1 field. Okay, so if you want to check this out, you're going to type in y1 equals to y over x, and you're going to use the alpha function to type in y over x. Then run the program slope, and I'll show this to you next time.